Welcome back. We're going to talk about least squares now. This is an important application of linear algebra. And the issue is finding approximate solutions to equations when exact solutions don't exist. So let's look at a very simple example. Suppose we had two equations and one unknown, 2x is equal to 1 and 3x is equal to 2. This obviously has no solution. So the question is, what's the best that you can do? And what we do is we view this as a vector equation. X times the vector 2, 3 is equal to 1, 2. That's exactly the same thing. And, well, this has a solution if and only if 1, 2 is on the line through 2, 3, which of course it isn't. So let's draw a picture. Here's the line through the vector 2, 3. And the point 1, 2, unfortunately, isn't on it. Well, the picture gives you the idea. What we should do is pick the point on the line which is as close as possible to the point 1, 2. That is to say, let's take the projection of the point 1, 2 onto the line. So that's part of the reason we were talking about projections in the previous lecture. So that is to say, we're looking for the vector x times 2, 3, such that this vector here has minimum length. And that is to say, if you write down the what it is we want to minimize, it's the length of this vector is 1 minus 2x squared plus 2 minus 3x squared. And, well, that's the length squared. And for that reason, this technique is called least squares. We're trying to minimize the sums of these squares. And this is called the least squares fit, or the least squares method. So let's write down the general picture along the lines of what we just said. So let's find the least squares fit to the following general set of equations, two equations and one unknown. a1x equals b1, a2x equals b2. Well, you write down this vector a1, a2, and we're looking at multiples of that times x. And we write down this other vector b1, b2, and we're looking for this projection. And I've labeled these vectors v and w exactly the way we did in the previous lecture, and x corresponds to the number c that we were using in the previous lecture. And so from the method that we had there before, we know how to find x. It's v.w over w.w. So that's the least squares fit. Let's just write this out in coordinates. It's the dot product of these two vectors and over the dot product of these two, which is to say a1 b1 plus a2 b2 over a1 squared plus b1, a2 squared. Okay, let's generalize this now. Let's look at more equations, but still just one variable x. So suppose we have n equations, a1x equals b1 down to anx equals bn. So we'll take w to be this vector a1 through an, and v is the vector b1 through bn, and we're looking to solve the equation x times w is equal to v. And if we can't solve it, we'd like to do the best we can. And again, we want to minimize the distance from this vector to the line. And the only difference is we're working in Rn now instead of R2. So the picture I'm going to draw is just the same, except that you should remember that this is in Rn. And the answer is exactly the same. X is equal to this dot product v.w over w.w. I'm just going to remind you here that the excuse me, book uses a slightly different notation. They write v.w as w transpose v, and over w transpose w, where we're writing these things as column vectors. But it's exactly the same formula. Okay, let's go on and let's generalize this further. Let's suppose we have more variables also. So let's say we had two variables, x and y. So then we'd have the first equation like this, a linear combination, a combination of x and y is equal to b1, down to a combination of x and y is equal to bn. So that is to say n equations and two unknowns. So we do something similar. We make an n by 2 matrix here out of the a's, and we're looking at this equation like this. So let's call this vector b and this vector x and this matrix A. And can we solve ax is equal to b? Well, one way to say it is we can exactly when b is in the column space of A. So pay attention here. This is an important point. If not, well, what do? So let W be the column space of A. This is a plane, a two-dimensional space. And that's the image of A, and this vector B is sitting somewhere, not necessarily in that plane, and we're trying to minimize the distance to the plane. So this point here is AX. This this point it's A applied to this vector X, and we're trying to minimize this distance b minus ax, and we'll solve that for x. So it's very similar to what we did before, except we're projecting onto a plane instead of a line. So how do we do that? How do we minimize this distance from b to ax? All right, well, something really neat happens here. So look at this vector b minus ax right here, this red line. What we're saying is that's perpendicular to the space W, which is the perpendicular to the column space of A. So that's how we find x. We want to check that b minus ax is perpendicular to the column space of A. Now, when you see perpendicular in column space, you say to yourself, what's this business with the 4 fundamental subspaces? Let's recall our favorite picture. A is this map from R2 to Rn. It's taking the plane R2, the xy variables, to this plane W. And over here on the image side, we have the column space of A, which is this image of A, which is this W. And we also have the null space of A transpose. And one of the key facts is that these two are each other's orthogonal complements. Okay, well, let's go back and look at what we were talking about. We're trying to find x so that this vector is perpendicular to the column space of A. Well, by what I just said, that's exactly the same thing as asking that it be in the null space of A transpose. The null space of A transpose is what's orthogonal to the column space of A. So therefore, you just have to check this equation. A transpose applied to this vector is supposed to be 0. So let's write this down. We're trying to find x so that A transpose applied to this vector is 0. That's to say A transpose B is equal to A transpose AX. We're trying to solve this for x. So it would be great if this matrix A transpose A, which is a 2 by 2 matrix, were invertible. Because if it was, we could just bring it to the other side. We could write x is equal to A transpose A inverse applied to A transpose B. So there you have it. That is the method of least squares. So let's summarize that. So the theorem is the following. You have A is an n by 2 matrix. And I want to assume that the columns of A are linearly independent. That is to say, well, there's two columns, and so the image of A really is a plane and not just a line. So let's make this assumption. The columns of A are linearly independent. Then the assertion is that this 2 by 2 matrix A transpose A is invertible. And because it's invertible, what's in the red box is legit. That gives the solution to the least squares problem. Okay, so let's go on and generalize this to more variables. So now we have m variables and n equations. And let's look at this equation here. So now we're looking at a map from Rm to Rn. And the image of A is an m-dimensional plane. Well, we can take it to be. If it's smaller, that's the degenerate case. But the interesting case is when it's an m-dimensional plane. And the picture is just the same because I can't draw any higher dimensional pictures, but it's basically the same idea. You're projecting now from Rn onto an m-dimensional subspace. And the theorem is exactly the same. The least squares fit is given by taking x is equal to A transpose A inverse, which is to say this matrix is invertible, times A transpose B. And I'm reiterating that I'm assuming here that the columns of A are linearly independent to make this true. And the error that you're interested in is this distance, the length of B minus AX. Okay, let's look a little more closely at this solution, or this point AX. So I was talking about X before, but X is this m tuple, but let's look at the image of it, this point AX. Well, X is this thing, A transpose A inverse times A transpose B. So AX is exactly this thing. It's A times all this other stuff. So that is to say, this matrix here, P, which is A times A transpose A inverse A transpose, this matrix is clearly a projection matrix because it's taking this point B to the point in the plane which is closest to it. That's exactly how we cooked it up. So it's worth checking this directly.
Yeah.
So let's see.
All right. I'll be done in a second.
Let's we want to check that P squared is equal to P. That is what a projection matrix is supposed to satisfy. Well, you write down P and then you write it down again, multiply it times itself. And the key thing here is that you can group these two middle terms together to make an A transpose A. And then the A transpose A and the following A transpose A inverse give the identity, so you can get rid of them. And what's left is A times A transpose A inverse times A transpose. And that's it. What I have here is P squared, and what I have over here is P. Okay, that's a good place to stop. And I'll see you next time.